Hi and welcome to Unit 2, Topic 3, Video 7. And in this unit, or this topic, and this video in particular, we're going to be talking about the identity of a matrix and leading into videos on the determinant and how we can use the identity and determinant and different contexts that we use them in. So let's start with some information about what an identity is. The identity of a matrix. In a number system we have multiplicative and additive identities. So the multiplicative identity is any number I. We usually just call the identity this sort of capital I, although you won't have seen it in a real number system, but you'll definitely see it in matrices. Any number I such that A times I equals A, where A and I are real numbers. So hopefully you recognise here that I is the number 1. We multiply 1 in order to keep a number the same. The additive identity is any number I such that B plus I equals B. So when we add, what do we add to get to itself? We add the number 0. So 0 is the additive identity in our real number system. Okay, but we're now talking about matrices. So the matrix multiplicative identity. Now the matrix additive identity, you might be thinking, are we going to talk about the additive identity? The additive identity is pretty boring. So for matrix A, which is let's say a 2 by 2 matrix, the identity to add to that, to get the same, is also a 2 by 2, and it must be equal to A 2 by 2. I, hopefully you've guessed it, is a bit boring, it's this. But the multiplicative identity is a little bit more interesting, and it leads to some work on inverses. So what matrix do we multiply by to get A from A? So let's say A is A, B, C, D. What is I such that A times I equals A? So let's have a think about that. What I'm going to do is I'm going to list I. And in fact, no, I'm not going to give you I. You can go and do some theory reading on this, and there's a generalization if you'd like. But actually, I'll show you this. Let's say A is A, B, C, D. It turns out that the multiplicative identity is 1, 0, 0, 1. What this does is in the first case, when we're multiplying, so we don't do that on the second one, in this case, when we're multiplying by 1, 0, it keeps the A and then it keeps the C, which is exactly what we want to happen. So AB times 1, 0 is just A, and CD times 1, 0 is just C. But when we multiply by the second column, which gives us our second column over here, it deletes the A and keeps the B. So AB times 0, 1 is B, CD times 0, 1 is D. And we get the same result as we started with. So I is equal to 1, 0, 0, 1. Now keep in mind here that it's a bit of a weird situation, but A has to be a square matrix, and I is also a square matrix. So I is 1, 0, 0, 1, that's the one you're going to use the most, but I could also be 1, 0, 0, 0, 1, 0, 0, 0, 1, or indeed it could be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, so on and so forth. It could be much larger than that. But you get the point here. It's all zeros except for that diagonal from top left to bottom right, which are 1s. I has to be square, A has to be square. So if we think about it, if A was not square, let's say A was a 3, 7 matrix, then we would have to multiply by I, and I would have to have 7 as its first dimension. Now, if we want this to be equal to A, I would then also have to have a 7 second dimension in order to end up with a 3, 7 matrix. But you'll see that this won't work out. We could do the 7 by 7, we could play around with this, but there would be cells that are missing, certain information that disappears, and we wouldn't end up back at A. So you can have a play with that, but it doesn't quite work. A has to be square and I is square. Okay, now let's talk about the inverse of a matrix. And again, we have inverses in our number system. And things get a bit funny here, so we have to be a bit careful. But for the number system, we don't have to be too careful because we know how this works. So inverses are numbers that bring us to the identity. And you've seen this and you've dealt with them before, and inverses are really important because you use them in equation solving. So if we have a number A, what do we multiply by to get to the number 1? Well, we multiply by 1 over A. That might seem a bit silly now, but if we do 7 times what equals that identity for multiplication, which is 1, We'll do 7 times 1 over 7. That gets us to 1. And what do we add to b in order to get back to I? Keeping in mind that in this case, I is 0, it's the additive identity. B inverse will be equal to negative b. So if we had 7 plus what is equal to 0, well, that would be negative 7. So we have an additive and a multiplicative inverse as well. We also have a matrix inverse, not all the time, but sometimes. So we have A times A inverse is equal to the identity matrix. And we can deal with that and find those inverses. But A inverse is not obvious, and it's not simple like it is up here. So these numbers, they just come naturally from that. It's not the same with matrix inverses. So I should go through and calculate one now, and then we'll finish this video on this example. So find the inverse of matrix A3201. Well, I know that I'm going to do A times A inverse, my apologies, is equal to I. Now I know A and I know I. So therefore A inverse must be the matrix that allows us to get I. And what I'm going to do is I'm going to say, well, I don't know A inverse. So I'm going to call A inverse A, B, C, D. Because the problem I have is that I can't just divide by A. You know, like the old, 7 times what equals 21? Well, you just divide by 7, easy. But I can't do that in this case because we don't know how to divide by a matrix. So instead what I'm going to have to do is do this a little bit more in a generalised form. So A times A inverse equals I, which means we have 3201 times by A, B, C, D is equal to 1001. And we know we can get cell matchings here. So let's do our 3201 times A, B, C, D. 3 times A and 2 times C. 3A plus 2C. 3 times B and 2 times D. 3B plus 2, it's funny again, so 3B plus 2D. 0 times A and 1 times C just gives me C. 0 times B and 1 times D just gives me D. So I'm going to do some matchings here, but I'm going to start in a clever way. The top two values, they're not so nice, but the bottom two values are great. I can already see that C equals 1. So the C equals 0. Done. And the D equals 1. I got a bit ahead of myself there. Done. So I've got values for C and D, which is great. And I'm going to use those in my next cell. So I might even just do a bit of highlighting. C equals 0. D equals 1. I'm going to use this is equal to that. In my next cell, I get 3A plus 2C is equal to 1. Now C is equal to 0, so I get 3A equals 1 and A equals a third. So that's not really a good third. Let's try that. A is equal to a third. Done. And then I need a value of B as well. And that is 3B plus 2D is equal to 0. So again, I'll highlight that and that. And 2D is 1. So I get 3B plus 2 is equal to 0. So D is 1. So 2D is 2. 3B is equal to negative 2. And B is equal to negative 2/3. And so there we have it. Which means that A inverse over here is equal to a third, negative 2/3, 0, 1. Now this is interesting because what I'm going to do is I'm going to just do this quickly. That's equal to 1/3 times 1 minus 2, 0, 3. Now this form will become really important later on. You'll see it and I'll explain what it is, but for now I'm just going to put it up there and show you, so you can refer back to this example if you want. Just before we finish the video though, extension, are there any other possible values for A inverse? Such that A inverse, and does A inverse A equal I also? So, are there any possible values for A inverse? Well, let's have a think about this. Did I do anything here where I had to make a choice? That's the thing. I've chosen A, B, C, D. C came out straight away. D came out straight away. A came just from C in that matching. B came from D in that matching. There's no moment I could have deferred to a different value. Therefore, it must be true. So the only way this could have happened is if I got these values. So I've now got the single case. A inverse is unique. It's the only one that can exist. And does A inverse A equal I also? Now, this is a pretty straightforward question. It's a one-off question, so I can just do the calculation. But the question about whether A inverse A always equals I is a little bit different, and we need to think about it. We've got square matrices, so our dimension mismatch is not a big issue. But I write it up as 1/3, negative 2/3, 0, 1, and I'm doing it on this side this time, 3, 2, 0, 1 there. Now, 1/3 of 3 and negative 2/3 there, that just gives me 1. 1/3 of 2 is 2/3, minus 2/3 times 1, that gives me 0. 0 times 3 and 1 times 0, that gives me 0. And 0 times 2 and 1 times 1, that gives me 1, which is I. So in this case, A inverse A does equal I. And I'm going to tell you that in all cases, A inverse A equals I. It's one of our rare instances where matrix multiplication is commutative. And if you watch my previous videos, you'll know what commutative is. Anyway, there's an introduction to inverses and identities for matrices. All the best.